All right, let's jump right into one of the biggest, most mind-bending questions in all of science. It's a question that was thrown down like a gauntlet nearly a century ago, and it came from a single paper that dared to look at the new world of quantum mechanics and ask, are we sure about this? It sounds like one of those deep, late-night philosophical questions, right? If a tree falls in the forest and no one's around, does it make a sound? Well, in 1935, three of the world's sharpest minds took that exact kind of thinking and aimed it like a weapon at the bizarre new rules of quantum theory.
See, on one hand, you've got the reality we all experience every day, the common sense world. A ball has a real position, a real speed, and if you kick a ball here, it doesn't instantly make a ball on the moon do something. But then you had quantum reality, which was saying something totally different. It said, no, a particle's properties are just a haze of possibilities until you actually look at them. And even weirder, two particles could be linked, or entangled, in a way that just completely defied logic.
So you've got this total clash between our gut feelings and the math of this new physics. It was a huge puzzle, and Albert Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, decided it was time to put that puzzle on paper for the whole world to see.
And this is it, the paper itself, published in May 1935. Just look at that title. It's not just some dry technical question, it's a philosophical grenade. They weren't just questioning the math, they were questioning whether this new theory was telling the whole story about what's real.
Okay, so if you're going to challenge a theory as big as quantum mechanics, you can't just show up and say, hey, this feels wrong. No way. You've got to set the terms, you have to define the rules of the game for what makes any theory a good one. And that is exactly what they did first. They basically said, look, any physical theory has to be judged on two big questions. Number one, is it correct? In other words, do its predictions actually match what happens in experiments? And quantum mechanics was nailing this part. But the second question, that's where they zeroed in. Is the theory complete? Does it actually have a spot for every single element of physical reality? To even ask that, they first had to define what real even means in physics. And this is their brilliant, absolutely crucial definition. They said an element of physical reality is any property of a thing, its position, its speed, whatever, that you can figure out with 100% certainty without physically poking it or messing with it in any way. And here it is, straight from the horse's mouth. This sentence is the absolute bedrock of their entire case. If you can know something for sure without having to touch it, then that something must be a real, honest-to-goodness property that was there all along. I mean, that just sounds like pure common sense, doesn't it?
So with that definition of reality locked and loaded, they built a thought experiment, a paradox designed specifically to put quantum mechanics to the test.
Let's walk through it. Imagine you have two particles. Let's just call them particle I and particle II. They bump into each other, get entangled, and then zoom off in opposite directions across the universe. Now, much later, we decide to measure the exact position of particle I. Here's the magic trick of entanglement. The second we know the position of particle I, we instantly know the exact position of particle II, even if it's billions of miles away. And this is the most important part. We did that without ever touching or even looking at particle II. So let's go back to their rule. We just predicted the position of particle I with 100% certainty, and we did it without disturbing it at all. Therefore, according to their own logic, that position must be a real element of physical reality. It must have had that exact position the entire time it was flying through space.
Now, if you actually pick up the EPR paper, you'll see pages that look like this, just packed with intimidating mathematics. But here's the beautiful thing. You don't need to understand a single one of those equations to get the point. The power of this argument isn't in the complicated math, it's in the crystal clear step-by-step logic.
And it's this simple, powerful logic that leads them to their absolutely shocking conclusion about the state of quantum mechanics. Because here comes the twist. This is the truly brilliant move. What if, at the very last second, we changed our minds? Instead of measuring the position of particle I, what if we decided to measure its momentum instead? Well, the exact same logic applies. By measuring particle I's momentum, we can know particle 2's momentum with 100% certainty, again, without touching it. So that means the momentum of particle 2 must also be a real, pre-existing element of reality. And checkmate, that's the trap. Their thought experiment seems to show that particle 2 has both a definite, real position and a definite,
real momentum at the exact same time. But here's the giant problem. Quantum mechanics itself, through the famous Heisenberg uncertainty principle, says that is absolutely forbidden. You can never ever know both of those things with perfect precision. So EPR's conclusion was inescapable. If these properties are real, and your theory says you can't describe them, then your theory must be incomplete. It's missing a piece of the puzzle.
They did consider the only other way out. Maybe the properties aren't pre-existing. Maybe our act of measuring particle I over here magically and instantly creates the position of particle 2 way over there. But for Einstein and his colleagues, this idea was just absurd. It meant some kind of signal traveled faster than light. He called it spooky action at a distance, and they basically dismissed it as being too ridiculous to be true.
So you see what they did? They backed physics into a corner, forcing it to choose between two seemingly impossible options. And by doing that, the EPR paper didn't end the debate, it truly ignited it for generations to come. Now, let's be super clear about this. The paper did not prove that quantum mechanics was wrong. In fact, here's the wild part. Decades of incredible experiments have now proven that the spooky action they thought was impossible actually happens. It's real.
So at the end of the day, the paper's real legacy was this. It framed a monumental choice for all of physics. Is it option A, that the quantum description of the world is incomplete, that there are hidden variables we just can't see? Or is it option B, that reality itself is non-local, that our universe is woven together in such a way that two entangled particles can influence each other instantly, no matter how much space is between them?
And what's just so mind-blowing is that this choice they posed in 1935 has now been answered. Reality is that strange. The spooky action at a distance that Einstein found so unbelievable is now the foundation for game-changing technologies like unhackable quantum cryptography and the race to build powerful quantum computers. So the question they left us with has evolved. It's no longer if reality is stranger than we can imagine. It's now that we know for a fact that it is, what other impossible things are we about to make possible?